Yeah, so just before we start this today's class, a brief review of what we discussed in the last class, or what we discussed. What is the last topic that we discussed? Anybody? Okay, so in the last class, we were discussing about the TLB and cache interaction. So again, whenever the processor tries to access the memory, first you have to get the address. The processor usually sends the virtual address, so you have to go to TLB, get the translation information, then you will get the address. From that address, you usually access the cache. Then you'll know whether it is a hit or a miss, and based on that, you either access the main memory or not. Okay. So these are some of the things. Again, last till this point, we were mainly discussing. If you are talking about the bigger topic, we are talking about memory organization. So we talked about how the memory is organized. Okay, so we talked about cache as the first level of memory, how the cache works, the different types of cache. Then we went on to a second level where we talked about interaction between your primary memory and your secondary memory. So that is where all of these concepts of about page fault, the virtual memory concept, the address translation, page table register. So all of these wordings we discussed, and all of these things we discussed till last point. Okay, still last class. So today I'll be starting with a new topic. Okay, so from now on for the next few lectures, so we'll be discussing about small topics related to the processor design. Okay. So one of the first topics that I'll start discussing today is called as advanced instruction level parallelism. Okay, so ILP basically stands for instruction level parallelism. Now, can you tell me what do you mean by instruction level parallelism? So I think if you remember some time back, okay, that is again when we first started discussing about computer architecture, general topics. So I discussed about parallelism also to some extent. So we discussed that there were three different levels of parallelism. Do you know what were those? What were the three different levels of parallelism? Anybody can remember? Again, it's been long time. I doubt if you would remember. System instruction, specifically not, we said something called as thread level parallelism. Okay, thread level, then you have, yeah, then we have the instruction level parallelism, which we called it as ILP. And then we also said that we have something called as hardware level parallelism. So thread level is basically a system level parallelism where you have many cores. You try to divide, you try to parallelize by executing different parts of the code onto different cores. Okay, so that is your thread level parallelism. Then you have instruction level parallelism where we try to overlap instruction execution. So we give a feeling that multiple instructions are getting executed at the same time. Even if it is having a single core, multiple instructions will be there in the same processor at different stages. So that is what is instruction level parallelism. And again, you have other meaning also. Multiple instructions can be executed at the same time, so that becomes your instruction level parallelism. And hardware level parallelism is where we try to parallelize the hardware implementation. The example that we gave here was ripple carry adder, where the carry propagates in a serial fashion, and then we have something called as carry lookup adder. So this is like a parallel implementation of the adder. Okay, so these are the different levels of parallelism. So our interest is mainly instruction level parallelism. How do you make make a circuit where, or make a design of a processor such that multiple instructions can be executed at the same time? That's what is here instruction level parallelism. To some extent, we have already covered instruction level parallelism. So what is the type of instruction level parallelism? So what is the technique that is used to achieve instruction level parallelism, which you have already studied about, which is like pipelining. Okay. So there are two primary methods of increasing the instruction level parallelism. Many try to increase the parallelism. To try to increase the parallelism, there are two ways that are followed. One is deeper pipeline. So first thing is you have to pipeline the processor, and you have to use a deeper pipeline. What do you mean by deeper pipeline? What could this mean? And why deeper pipeline will give you better parallelism? So deeper pipeline is more stages. Okay, more stages. So we have discussed about a processor which had 5 stages. Okay, now why do we say that having more stages, okay, more stages will improve the performance? Will increase the parallelism, that will increase the performance. More instructions in parallel. Okay, so something specific we discussed about speed up, no? So what was the ideal speed up that we would get in a pipeline processor? What will be the ideal speed up? We have discussed about this also. What is the ideal speed up that we get in a pipeline processor? It is equal to number of stages. Okay, it is equal to number of stages. So if you have more stages, this is ideal. This is ideal meaning what you say, the number of instructions should be very high and the stages should be balanced. Okay, stages should be balanced. So all of these, if they are satisfying, then it's called as ideal case. So in the ideal case, your ideal speed up will be equal to total number of stages. So if you increase the number of stages, you will get an increased speed up. So that is why we say that to increase the instructional parallelism, one way to do it is deeper pipeline. Now the other way that is like overlap more and more instructions. More instructions will be in parallel as somebody explained earlier. Okay. Then we have another technique which we call it as multiple issue. Okay. So multiple issue processors are those where you replicate some of the internal components so that it can launch multiple instructions at the same time. Okay, what do you mean by launch multiple instructions? Normally, if we take a simple 5-stage pipeline processor, you have these stages: instruction fetch, instruction decode, then you have execute, then you have memory, and then you have write back. Okay, so these are the different stages that you will have, and instructions can be there in different stages. Now, at a time, only one instruction can be fetched here. Okay, in the Python processor that we have discussed. So here, whenever I am able to fetch only one instruction at a time, so that is basically called as single issue processor. Okay. Okay. Issue has a different meaning in an advanced architecture sense, but we'll not. We'll try to simplify this, and we'll assume that issue is basically how many instructions will you be able to fetch at a time, and then decode and so on. Okay. So it's like a single issue processor. Now, if I replicate these components, okay, let's say I have a processor where there are two IF blocks and there are two ID units and there are two execute units, or there can be execute and mem, which can work in parallel, and then there is write back. Okay, so there are two write back units, two instruction decode units, two instruction fetch units, but in the third stage, you either have execute or memory. Okay, so some of the components are replicated here. So this way you'll be able to launch two instructions depending upon what they belong to. So for example, R type instructions can be launched here, and parallelly at the same time you can fetch and try and execute load store type of instructions. Okay, so that is possible here. So such processors are called as multiple issue processors. Okay, multiple issue processors. Okay, so in multiple issue, what happens? You replicate internal computers so that it can launch multiple instructions at the same time. So here, normally in a normal pipeline processor, in a single cycle processor, your CPI will always be greater than 1. Ideal CPI will be equal to 1, but the actual CPI will be greater than 1. Okay, but in the case of multiple issue, multiple instructions might be executing in a single cycle. So in that case, your CPI will be less than 1. Okay, so depending upon how many instructions can be fetched and executed parallelly, you will typically have a CPI of less than 1. In that case, they use one more parameter called as instructions per cycle. So how many instructions I am able to execute per cycle is another parameter that they use to measure the performance of multiple issue processors. Okay. So if I take an example, let's say there is a 4 gigahertz processor and it is having a 4-way multiple issue. Okay, so 4-way multiple issue meaning you will be able to fetch 4 instructions at a time. You will be able to decode 4 instructions at a time and so on. So if you have 4-way multiple issue, then this will lead to a CPI of 0.25. Okay, meaning assuming there are no memory stalls, there are no stalls due to branch conditions. So assuming that there are no stalls, So ideal CPI is one for single cycle and simple pipeline. But in the case of multiple issue, if you are able to issue 4 instructions at a time, then 4 instructions can be executed in a single clock cycle. So if 4 instructions are executed in a single clock cycle, the CPI will turn out to be 0.25. Or IPC is one other parameter that will tell you this kind of information, which is 4 here. 4 instructions you'll be able to execute in a single cycle, provided that you don't have any stalls and so on. Okay. So this is another parameter that they use for multiple issue performance measurement. Now, multiple issue, there are 2 types of multiple issue processors. So one is called as static multiple issue, where majority of the work is done by the compiler. The compiler groups instructions that are to be issued together, and then those instructions are they put those instructions as a single packet. Okay, so the packet they package them into something called as issue packets, and compiler basically detects and tries to avoid the hazards if there are any, because when you are trying to fetch 2 instructions at a time, execute 2 instructions at a time, there will always be more possibility of hazards. Okay, so that's uh, compilers what do you say main job to avoid these hazards and make sure that there will be no problem while execution. Okay, and there is something called as dynamic multiple issue also. So here majority of the work will be done by the CPU. Okay, so CPU chooses instructions to execute in each clock cycle, and the compiler might help in reordering. It's not that the compiler will not do anything; it might still help to reorder the instructions so as to minimize the possibility of hazards. But the actual grouping of instructions that are to be executed will be done in the hardware itself. Okay, so it's a CPU who resolves the hazards by having a forwarding unit, by having a hazard detection unit. So all of that will be implemented in the hardware. Okay, so that is an example of dynamic multiplication. So now we'll try to see different processor types where you might have this. Okay, so first thing is we'll try to see how a dual issue processor might look like. Okay, so this is static dual issue processor, meaning majority of the work will be done at the compiler level. At hardware, you just replicate the components. Now, initially, we'll discuss a single cycle version. Okay, we'll discuss a single cycle version, and then we'll see how the pipeline version might look like. Okay, so we'll assume that there are 2 issue packets. Now, issue packets will group in such a way that one of the instruction is ALU or a branch instruction. The other instruction is a load, store instruction. Meaning, as I told you, right, there are 2 IF blocks, there are 2 ID blocks, but then there is one EX and one memory which can work in parallel, and then you have 2 write back. Okay, so meaning what do you mean by having 2 ID stages and 2 write back? Does it make sense? Because the register file that you are accessing will always be one only. So can you tell me what do you mean by this having 2 ID stages or 2 write back stages? How will you modify the register file to accommodate this? Any ideas? 2 access are allowed, no, already. So what you have to do is you might have to come up with some kind of register file where you will be able to read 4 registers at a time. Okay, so read 4 registers at a time. Just like you read 2 registers at a time in the normal case, here you should be able to read 4 registers at a time, and you will be able to write into 2 registers at the same time. Okay, for example, in one of the cases, you will have some ALU instruction, let's say add. In other cases, if you have load instructions, so both of these instructions will write something into the register. So if you are using the same register file, you should allow for 2 writes to the register file. Okay, so this is one modification that you have to look at. When I say 2 IDs and 2 write back stages, it's not that you have 2 different register files. You have the same register file, but you give more number of ports to it so that you will be able to read more and write more. Okay, you'll be able to read 4 registers parallelly instead of 2 as per our earlier case, and here you will be able to write into 2 registers at the same time. Okay, so that is what I mean by replicating. It's not that you have a copy of the same unit. It's not that you would have two different register files. Okay, so that you should be very clear about. So let's assume that there are two issue packets that goes into this dual issue processor. One of the instruction can be of ALU branch type. The other instruction can be of load store type. So, and again, sometimes both of them you might not be able to use at the same time because of some data dependency. In that case, the one which is not used, you have to pad it as a NOP instruction. Okay, I'll show an example to make it clear. Okay, so now this is how typically the execution might flow. So since it is single cycle, so in the first clock cycle, you'll be fetching two instructions at the same time. Of course, these two are shown as different here, but they can work parallelly also. Okay, it's not like you are having unnecessarily one extra memory stage because ALU branch will not need memory, right? You can always put memory here instead of here. Okay, so this is like one way to represent. But again, just to make sure that you follow the same representation, they have used this kind of representation. Okay, so the first clock cycle, two instructions will be fetched, two instructions will be decoded, and they will be executed. After those two instructions are completely done, only then the second instruction will start. The second set of instructions will start getting fetched, getting executed, and so on. Okay, so that is what you mean by dual issue. Normally, in the single cycle, single issue, what would happen is you would not have this. Okay, this is a single instruction, and again after that you would have a second instruction getting fetched here. But now, since it is a dual issue, parallelly two instructions can be fetched, two instructions can be decoded, and so on. This is a single cycle. The pipeline version also will look very similar. So if you take the same example of two issue packets, one packet accommodating ALU or branch instruction, the other packet accommodating the load store. Sorry, one slot being accommodated by ALU branch, the other slot in the same packet accommodated by load store. So this is how it would look like. It's very similar. Only thing is, in a single clock cycle, two things are happening. Okay, so that is how the execution might look like. Okay. So just for avoiding confusion, we'll not put them in parallel. We'll assume that the EX will happen and it will have an empty slot, and then here mem will happen at a much later point. So that again, some data dependencies are resolved without requirement of stalls. Okay. Okay, so if you have more instructions executing in parallel, then there is possibility of hazards also. So forwarding can avoid stalls. Forwarding was used to avoid stalls in a single issue. So for example, in this case, but here how do you avoid? Okay, so for example, here you are supposed to calculate T naught, and only then it is supposed to use it in the next instruction. So now you can't actually put them in the same slot. Okay, you can't use ALU result in load store in the same packet, because first it has to execute, T naught should get updated, and then only T naught can be used. So both of them cannot be put up in the same slot. So the other case is something like this. So here your S2 is getting loaded and the same is being used in the next instruction. So the next instruction after load cannot use the result without stalling. So this at this point, maybe forwarding can be implemented, but this cannot be avoided because memory will happen later, and then you might have to forward that value. Okay. So in these cases, you might have to either stall, or you might require a little more aggressive scheduling so that these cases will not occur. You try to separate them such that this goes into a different packet and this goes into a different packet. Okay, so now let us try to take an example and see if we can schedule it. Okay, now your main objective is you are a compiler. Okay, now when you are a compiler, if your main objective is to group the instructions, group the available instructions into packets, and then tell the processor to fetch these instructions at the same time. Okay, now this is a small code that I have given. So can you tell me how do I schedule this? Let's say there are two slots in each packet. Okay, so I'll call them as issue one, just like we say clock cycle one, clock cycle two. So here we'll say issue one, issue two. In each issue, you will be packaging two instructions belonging to two different slots. So one slot being an ALU or branch type instruction, the other slot can have load or store instruction. Now, can you tell me how do I schedule? What will come in issue number 1? The first issue slot, which two instructions can I group? Any idea? Or it's not possible? It's not possible to group two instructions. Can you tell me why? Why you can't group two instructions? So can you tell me, can I group these two instructions at the same time? Can I group these two instructions at the same time? No. Okay, why? Because there is a dependency on T naught. Okay, so T naught is a dependent, and again there is a T naught dependency here, so I can't group these two. Okay. Now add I can group it along with load. Okay, that is one option, but then it can go in many places. Okay, so the add I can go in many places, but you are changing your S naught, and here S1 is being used. So that also you have to remember. Okay, so that's why the scheduling will look something like this. In the issue 1, the ALU slot will not have anything. You just schedule the load instruction. So what will come in the second issue? Any ideas? Can you tell me what would come in the second issue? Add you mean to say. But can I have add here? You remember, we are using this, we are just replicating. So we are not trying to parallelize. Imagine I am just replicating this IF, ID, EX, mem, the entire stage. Okay, right back. I'm just replicating such that there are two such units available. So this is like the processor that I have. Okay, assuming this is the processor that I have. After load instruction, in the immediate next slot, can I schedule add? Yes or no? Why? Can you tell me why? Okay, yes, somebody says. So again, we have been discussing, no, when there is a load followed by data dependent instruction, let's say it is writing into T naught and the next instruction is using T naught. In this case, can this be resolved by forwarding? It's pipelined as well. Assume it is pipelined as well. I'm discussing about pipeline. Okay, so I'm discussing about pipeline. So in this case, can I solve this with the help of forwarding? No. Whenever there is a load followed by data dependent instruction, there is always one stall involved. Okay, we have discussed that in the pipeline processor extensively. Okay, so in that case, I can't schedule add you here. So one possibility is you can have NOP and NOP here, but the other possibility is I'll try to execute this instruction much before. Okay, I'm executing add a instruction here itself. Again, there are issues with this. So how do what will be the issue if I execute this before? Okay, so before these two instructions, I'm executing add I S1, S1, -4 here. What will be the problem if I do that? So your store location will be wrong. So if I assume S1 is also 0, okay, or let's say S1 is 8 initially. So you're supposed to access location 8 and location 8 here. But if I shift this instruction, here S1 is changing to 4, and here you'll be accessing 4 location instead. So is there a way to correct this? I don't want to change this issue. I still want to utilize this slot. So now if I use this exact instruction, then I'll be accessing a location which is 4. Okay. So what would I have to do if I have to change this? So you just have to change this 0 to 4. Okay, so that way S1 will have 4. You add a 4, then you'll be accessing location 8. Okay, so that is one way you can modify this. Okay, so that we can do later whenever store is getting executed. So now what will come next in the next issue slot? The next issue slot, what will come? So in the second issue, I have add a instruction and load store. Nothing is there because I cannot execute store here because your T naught is still not ready. Okay, and T naught is supposed to be modified by add. So what will I execute in the next issue slot? Add is already done. Okay, add is already done. So in the next issue, I will be executing add you. But again, I'll not be utilize load store because store still requires this value to be known. Okay, so once you execute this instruction, and then in the next instruction, in the next issue slot, what can I schedule? So here I'm executing only load. In this instruction, I'm executing add I. So S1 is getting modified. The next instruction I am getting executing add U. And what about issue slot 4? What can I execute here? What can I execute in the issue slot in the issue 4? Store alone, and BNE, because you have this slot empty. No, here ALU or branch can be executed. Here load or store can be executed. If that is the case, so you execute your BNE instruction here and your store instruction here. Okay? So this is how the issues can happen. Normally, how many clock cycles would you require to ideally? Okay, so don't worry about the extra overhead. So if there are 1, 2, 3, 4, 5 instructions, so normally, ideal case, you might require 5 clock cycles. Of course, it will be 5 plus something. It will be 5 plus 4 to be exact. But let's not worry about this 4 for now. Okay. Now, if I talk about each issue getting executed in a single clock cycle, I am ending up with 4 instructions. So ideally, it will be 4 plus 4. Okay. But again, if you remove, if I keep on increasing the number of instructions, so this will become negligible when you compare it overall. So if you neglect that, then you have reducing only one cycle. So is this an improvement? So you are copying the data path, entire data path twice. So even then you are getting only one cycle advantage, not a big saving, no? Is that correct? Or do you think it will help? So for many instructions, it would help. Okay, so one more thing that would help is you can actually again, I'm giving you another solution. So I can execute add I after this only. At the same time your load is executing, you can execute add I. So that way everything else will remain. Only thing is here nothing will be done. Okay, so add I can go here or here depending upon what you want. So both solutions would still be correct. Okay. And remember, I have changed your S4 here. Okay, the S1 value was changed, right? So hence I am using the store instruction, but here I have a 4. So you know the reason why there is 4 here. Add is add unsigned. Add unsigned. Again, don't worry about this. You can assume it as simple add instruction. Okay, add U is basically add unsigned. Okay, but don't worry about this. It's assume this is an add instruction. Okay, so the second solution I gave you is add I executing in the first issue slot, and in the second issue slot you don't have anything. You have a NOP operations. Okay. Now, yeah. So this is how the execution typically happens. Now, when you are dealing with loops, okay, when you are dealing with loops, you are supposed to execute these instructions again and again. Meaning you have to keep issuing the same packets again and again. Okay. Instead of doing that, what the compiler tries to do is the compiler tries to use a technique which is called as loop unrolling. Okay. Loop unrolling is a concept which is a compiler concept where it will try to unroll the loop and see if we can get an advantage. We'll try to do that. So here 5 instructions were there. Okay, now you can reduce that to 4 issue slots. So maybe one cycle you are getting benefit. But if you loop unroll, you will get even more benefit. Okay, so we'll try to see how that is done. Okay, so let's say it's a compiler technique, loop unrolling. So we'll assume the loop index as 4. Okay, what do you mean by loop indexes? How many times you want to replicate this loop? Okay. So again, there is a difference between the number of times the loop should run and loop index. Okay, let's say this loop is supposed to run maybe 16 times. Okay, this loop is supposed to run, let's say 16 times. So in that case, when I say loop index 4, what I'll do is I'll replicate these statements 4 times. Okay, so there'll be 4 loads, 4 adds, 4 stores. Okay, and maybe this is like an overhead. You will be doing it only once. So you are basically loading some element, adding some value to it, and storing it in the same location. That's what is being done. So this, let's say it is supposed to be done 16 times for 16 different memory locations. So that is as good as saying that if I say that loop index is 4, I'll replicate these statements 4 times. But then how many times this should get executed? If I replicate the statements 4 times, how many times this entire group should execute now? It should execute 4 because individual instructions will be replicated 4 times. And then the whole loop is supposed to be for 16 times. So this group will have to be run for 4 times. Now, if it will work out if the number of times that the loop executes is a multiple of loop index. Now, what if the loop is supposed to run 15 times alone, 15 times only? How do you manage that? What happens if your loop is supposed to run 15 times only? How will you take care of that? Any idea? NOP instructions? No. Last as NOP. Okay, no, because see, this entire group, you should think of it as a group. You can't divide this. So this entire group can run either once, twice, or so on. So it can't run 4 times because that way it will exceed. The maximum this can run is 3 times. Okay, then if it runs for 3 times, it will be 4 copies into 3, which will be 12. You are still left with 3 more loops. How do you implement those 3 more loops? So normally what they do is they'll execute the loop unrolled part these many times. How many times? So that will get by taking 15, then you divide it by the loop index. You take only the quotient part. Okay, the quotient, don't take the remainder or don't take it as a fraction. So if I divide 15 by 4, the quotient part will be only 3. Okay, and then you are left with remainder. Okay, so this remainder times you have to execute your original loop. Okay, so this original loop will be used to execute for the remaining 3 times. So that is how the loop enrolling is achieved. But you don't have to worry about those things as of now. We are just trying to see for initial discussion, we'll try to assume that the number of times the loop should execute is a multiple of loop index, and then we'll have a discussion. But normally the loop unrolling is implemented this way. Okay. So suppose if I want to execute, let me give an example. Let's assume that loop index is 4. Now, I'll unroll the loop. So there are 2 blocks. One is unrolled block. Okay. And then is the normal block. Okay. Unrolled block and then the normal block. If I am supposed to execute it maybe 23 times, the actual loop. So how many times should the unrolled loop execute and how many times should the normal block should execute? So can you tell me from this? Keeping loop index as 4. So it will be 5, 5 4s are 20, and the remainder is 3. So this is how you actually do it. Okay. So now let's assume the loop index as 4. So you have to typically make 4 copies of the loop body. So let's try to make the 4 copies of all of these instructions. But again, all of these instructions are not required. Only the instructions which are actually doing some operation. You have to replicate only these as 4 times. The other things like there is branching or adjusting the pointer can be done only once because you are executing this 3 times. So what you do is you adjust the pointer all together at once. For every cycle, you need not update the pointer. Okay. So you will use that concept. So when I try to replicate, the first instruction is load from some memory location, right? So when I say replicate, should I replicate this way? Should I replicate this 4 times? Load T0, 0 S1. So load T0, 0 S1 and load T0, 0 S1. When I say replicating, is this what you mean? So what do you mean by replicating? So you replicate in such a way that normally this would have access to only one location. You replicate instructions such that it will access the next locations. So you see how the loop is executing. So S1, if S1 is let's say some 24, let's say decimal. Okay, so initially for the first location, first loop iteration, 24th location will be accessed. In the next iteration, S1 gets subtracted by 4. So 20th location will be accessed. and then 16th location will be accessed, and then 12th location will be accessed, and so on. Now you have to replicate in such a way that these four are done at the same time. Okay, these four are to be done, meaning you have to access 24th location, 20th location, 16th location, and 12th location. Okay, so how will I be able to do that? I'll be able to do that by modifying this constant. Okay, so when I modify this constant, the four instructions could be -4 of S1. So this will get me 24th location. This will access the 20th location. This will access 16th location, and the next one will access 12th location. But is this still correct? There is still something wrong, no? Here, what is wrong? What is wrong here? So this is how you typically replicate, but it's still something wrong here. Can you tell me what is that? So all are loading into T0. Okay, so you are storing this also in T0. When you store the second element, the old element will be lost. If I try to store this, then these two elements will be lost. So how do I rectify this error? How do I rectify this error? So I'm telling you how actually the loop is unrolled. Okay, so initially I told you that loop is unrolled 4 times, but how exactly it is done? Okay, that I am trying to explain. So first thing is your memory locations will get updated according to the the pointer updation. So initially you are subtracting the pointer by -4. That's why your locations will all change to -4, -8, and -12. But then you are supposed to get that element. So what I'll do is I'll not use the same register. I'll have to use different temporary registers. Okay, I have to use T1, T2, and T3. Let's say T0 is the one that was used earlier. So when I say replicating each statement, you have to take care of all of this. It's just not blind replication. Okay, so you have to adjust your pointers according to how the loop is progressing, and you have to make sure you have to use multiple temporary registers because you have to accommodate the new values. Now, what will be the next instruction? So this we tackled about this case. Okay, so we have tackled this. So we replicated this 4 times. And if I want to replicate this 4 times, what do you have to do? So if these are your initial instructions, so the add instruction, if I want to replicate, it will be add T0, T0, S2. This was your original instruction. Now, if I want to modify the next location's data, you can say T1, T1, S2. Then the next location is T2, T2, S2, and so on. So this is your second instruction that is getting replicated. Now the storing part. So you are taking 4 elements at a time. You are adding, you are modifying your 4 elements, and then you are supposed to store back those 4 elements with the help of store instructions. So your T0 gets loaded into 0th location, meaning 24th, 20th, then 16th, and then 12th. Okay, so this is how your memory locations will be accessed. Now about the adjusting of the pointer. Now, normally in each loop, you would have adjust the pointer with the help of this instruction, add S1, S1, -4. So this was the pointer adjustment that you had done earlier. Now you are replicating the loop 4 times, meaning you are doing 4 operations at a time in this entire block. In that case, how much should I adjust my S1 pointer now? So what's the statement that I have to use? Instead of using this 4 times, I can always replicate that also. I can say add I S1, S1, -4, add I S1, S1, -4. But there is no need to do that, right? So all these 4 statements can be combined into one. So what is one statement that I have to use for adjusting my pointer? We can directly say add S1, S1, -16. Similarly with the loop, I don't have to check the loop every time loop condition. I can check it once at the end. Okay, and then if it is exceeding, then I can come out of the loop and then carry on this further. Okay, so this is what you mean by loop unrolling. You don't just replicate the statements, you modify the program, but the overall functionality should not change. Okay, but you might have to use more number of temporary registers, and you might have to alter a few things in your code. Okay, but the actual operation will not change. The actual operation will still be the same. Okay, so this is what is called as loop unrolling. So this is used in many things. Here I'm explaining this with respect to multiple issue, but loop unrolling is a very powerful concept which is used in your GPUs as well to implement loops. Okay, so what they do in GPUs is they'll replicate like this, and then they'll schedule all of these onto different cores. Okay, so that is how it is typically done in GPUs. Okay, it's a very powerful concept, loop unrolling. Although I'm explaining it with respect to multiple issues, don't think that it is only applicable here. Okay, so you'll find this in many places if you study few advanced concepts of computer architecture. Okay, now this is the loop unrolling part. Now I have unrolled the loop. Okay, now if I want to schedule, okay, I want to schedule these instructions and see if you will get any advantage. Okay, so normally if I executed the same loop, earlier loop 4 times, okay, so if I executed the same thing 4 times, and you saw that there were 4 issue slots required. So 4 times into 4, you would have required 16 issue slots to execute the program. But here we will try to see the advantage. Remember this thing. Okay. So if I am supposed to execute this loop 4 times, we have scheduled this 5 instructions into 4 issue slots earlier when the loop was not unrolled. 4 issue slots, and if you are supposed to execute this 4 times, there will be 16 issue slots required. Okay, I'm just talking about 4 times execution. Okay, if you keep on higher execution, then it will be the advantage will be even more. But let's assume that 16 issue slots are actually required. But once I unroll the loop, okay, once I have unrolled the loop, now we'll try to see how to issue the instructions. Okay, now I'll again assume that there is an ALU slot, a load store slot, and the issue number. Now you tell me what happens in issue number 1, which instruction should I schedule, and so on. So can you tell me first issue slot, what should I execute? Load T0. Okay, so load T0 will be issued in the first issue slot. Only load, or do I have anything else that can be issued here? Only load. Okay, so this is your issue number 1. Okay, issue slot 1. What about your next issue slot? Can I execute anything here? Only load again. Okay, so you'll not be able to execute anything. No, add you cannot execute. Why can't you execute add here in the next issue slot? Again, yeah, go back to our pipelining concept. Load followed by data dependent instruction cannot be, should have a stall in between. Okay, should have an issue like one empty stall or one NOP in between. So I can't schedule it here, okay, in the second issue slot. So then I can issue only load T1 here in this second issue. Now what about third issue? Third issue. So now you can implement add T0, and then you can also implement add load T2. Okay, so load T2 and add T0, because now between this instruction and this instruction there is one slot. So this way there will be no hazard. Okay, so this is your issue number 3. Now what about issue 4? Issue 4. And from this you should be able to tell me easily. Okay, so then you can issue add T1 and then load T3. Okay, so this is your issue 4. What about issue 5? Issue 5, add and store. Okay, so I can now start storing, because now this would have already completed. I can start scheduling my add instructions along with the stored instructions. Okay, so issue slot 5, issue slot 6 also, it will be add T3 but store T1. Okay, and now what next? So this is your issue 6. What about issue 7? Issue 7. Issue 7 will be only store, but again, I can schedule add-I also, but again, add-I can be done either here or next. Okay, so both solutions would still be correct. Let me modify my S1 here itself. If I modify S1 here, what will happen? The next slot I can actually both I'll be able to do. That way I think I'll be able to save one extra slot. But only thing is here you have already modified your S1. Okay. So normally you should have done -12 S1, but you have already changing your S1 by -16. In that case, how do I modify this instruction? What should be the correct instruction that I'll execute here? The correct instruction that is to be executed here is in issue slot 8, store T3, 4 S1, because you are modifying your S1 here itself by -16. So to this, you have to add 16 to correct it. So that way it will be 4. Okay, so that way it will be 4, and this is how the number of issues will be there. Okay, now do you see an advantage? What is the advantage? Earlier I said if the loop index was 4 and if the loop is supposed to be executed 4 times, 4 times into 4 issue slots, so you require 16 slots. Okay, issue slots. Now, if you are able to loop unroll it, you are able to execute it in 8 issue slots. Okay, so you see 16 to 8. There is a reduction by half. You see now the advantage of loop unrolling. Why do you think it happened? How we knew to unroll for? Yeah, no. We did not know to unroll the loop. This is fixed by the compiler. Okay, the loop index is something which is fixed by the compiler. Based on that, we unroll the loop. It's not something which is decided on the fly. Okay, so it will be built in the compiler. So whenever it starts unrolling the loop, okay, it will fix a number. It will either like it will fix a number, and most of the times the loop unrolling will happens in multiples of 2s. Okay, there is a reason for that, but again, I don't want to get into that now. But this loop index, either 4 or 8 or 16, will be fixed by the compiler before only. It's not decided on the fly. What if S1 was originally 12? Originally 12, meaning I didn't get it. Your original program, it's not like you're modifying the program, no? You're executing the program. Then again, the loop controlling will not be done in that case. I told you, right? It will first take the number, divides by loop index which is fixed. And if you get a quotient, okay, if you get a quotient, that many times the unrolled loop will be executed. Okay, and the remainder times the normal loop will be executed. Okay, in your case, what you say 3. 3 divided by 4 will result in what? 0. So this will not be executed at all. The unrolled loop will not be executed at all. Only the normal loop will be executed. That too, it will be executed 3 times. That is how the execution is done. Clear? So you see the advantage. So by just unrolling the loop, you are getting half the advantage. You are saving half the number of issue slots. So that's the power of loop unrolling. Okay. So now I said that the loop unrolling, the index in the loop unrolling is typically fixed as multiples of 2. Now, can somebody give it a thought and tell me why do you think that is? Again, Vignesh, you don't answer this. Let others answer. Why do you think? Again, I just told you, right? Oh, sorry. Why is it powers of 2? Not multiple of 2. Sorry, my bad. So it should be power of 2. So it will the loop unroll loop index. Okay, loop index is either 2 or 4 or 8 or 16 and so on. Why is that? Anybody? Give it a thought. Give it a thought. If I am the interviewer, I'm asking this question. Okay, so in loop unrolling, I'll always choose a loop index as a power of 2, not multiple of 2. Sorry, for my mistake. Earlier also, I think I told it as multiple of 2. That is incorrect. So it should be powers of 2. Why do you think that is? Saving time on branch evaluation. No, nothing related to branch. Why should I not choose my loop index as 3? The same concept can be applicable here. No, let's say the total number of times the loop should be executed as 16. If I divide by 3, I'll get some quotient. So here the quotient will be 5. So 5 times I'll execute the unrolled loop. Okay, unrolled loop, and the remainder, which is 1, I'll execute the normal loop. Here also it is applicable. Why will I not choose 3? Instead, why will I choose it as 2, 4, 8, and 16? Nothing to do with girl issue. Girl issue is totally altogether different thing. Memory is indexed in multiples of 4. That also doesn't matter here because you can just stick to only 3 cycles. No, you can have 3 loads, -4 and -8. So next time I'll update my S1 such that this is taken care. That also is not the correct answer. Think about it. Anybody? The thing is with this, okay, so here to check to know how many times the unrolled loop should be executed, how many times the unrolled loop should be executed, and how many times the normal loop should be executed. So for that, you are doing a very complex operation. Okay, so you are first taking the number of times. Let's say n is the number of times you want n divided by 4, and you also want n percentage 4. So this is very costly operation. Okay, if there is some other number here, but if you have the number to be power of 2, okay, why do you think you get an advantage? Let me show you with an example. Let's assume this is some 23. Okay, so 23, how do you represent in binary? 1, 2, 4, 6, sorry, 1, 2, 4, 16, 32, and so on. How do you represent 23? 23 will be 1, 1, sorry, okay, 8, and then 16, sorry. So 1, 0, 1, 1, 1. Okay, so this is how you represent 23, right? So 23, how many times the normal loop should be executed? So that will be equal to 5, okay, because 23 divided by 4 will result in 5. 23 percentage 4 will result in 3, okay. Now, is there any way that I'll be able to get these two values from here directly without actually doing this operation? Anybody? Carefully observe, okay, carefully observe. So where is this 5? This 5 is here. Where is this 3? This 3 is here. If you just take these numbers, if you just right shift, or if you just directly, not even right shift, wired shift, if you can do, you just take these three numbers, that will give you how many times the unrolled loop should be executed. And the lower LSB bits will tell you how many times it will basically give you the reminder. So if you are dividing or trying to get a reminder for a number, when you try to divide it by a power of 2, or when you try to get a reminder when you are trying to divide it by power of 2, it's as good as just extracting the bits. Okay, so here you are extracting 2 bits. Had the loop index been 8, okay, had the loop index been 8, okay, so 23 by 8, how much would that be? 2, and then 23 reminder will be 7. So where is this 2 and 7? That also is clearly visible here. Okay, so 2 is the first two MSB bits, and 7 is the last 3 MSB bits. So depending upon how much is this value. So if it is 4, okay, so if it is 2 power 2, I'll take the last 2 MSB bits as the reminder, and the remaining MSB bits as the last 2 LSB bits as the reminder, and the remaining MSB bits as the quotient. Same thing here. So this is represented as 2 power 3. So 3 bits, 3 LSB bits, I'll be taking it as reminder. Okay, so now this becomes reminder. So if I am talking about 1, 0, 1, 1, 1, so this becomes reminder, which is 7, and this becomes your quotient, which is 2. Okay, so that's the reason most of the times, not most of the times, all the time, the loop index and loop index for while loop unrolling will be in terms of powers of 2. Okay, so this is something which we generally don't discuss, but I thought you should know this also. Okay, so loop unrolling has this advantage where the issue slots get filled. So if you see earlier, there were cases where nothing was put in ALU slot, nothing was put in load store. But here, in each and case, at least one slot is getting filled. So that is how the advantage the advantage of loop unrolling can be exploited, and you'll be able to issue the instructions in less number of issue slots. Okay. So I think with that, I'll stop here. If you have any doubts related to any of the topics that I discussed, please let me know. Okay. So we continue this discussion. So this is static multiple issue. In the next class, we'll talk about dynamic multiple issue. Okay, just the basic behavior part I'll be explaining, because dynamic multiple issue processors itself are very complex. You need to know a lot of concepts related to that. Okay, we'll just give you a gist of dynamic multiple issue. Okay, so this is basically a static multiple issue processor that we discussed, and with loop control. Okay, so that's all from my side today. Okay, so what is the doubt in the assignment?
Sir, in the assignment, it doesn't explicitly mention a control unit. So
Hmm.
adding a control unit would make the whole code a bit more modular. So do we add a control unit, or do we stick to the subunits mentioned?
No, 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 no. So I did not say that you should implement only those subunits, right?
Yeah.
Did I
Okay.
mention it somewhere that you should implement those subunits? So I just asked you to copy the codes for those units. It
Okay.
doesn't mean that other units which might be required, you should not implement. Control units should still be implemented.
Okay.
Okay.
That was it.
Yeah. Any other doubts related to this class or anything else? I did not. I thought I did. Let me. Yeah, if I'm not done that, I'll do it.
Sir, you by mistake uploaded the PowerPoint presentation in the lecture videos, like
Okay. Sorry,
lecture
sorry,
videos.
sorry, sorry, sorry. Okay, I'll do that. I'll do that. Thank you.
Thank you.
Yeah, I hope you have received the email regarding the labs, right? Okay, so people have left. Anyway, thank you. Okay. Yeah, so that's all from my side today. Thank you.